All right, so I'm now recording. All right, so today's the last topic, okay, which is transformers. Now this isn't, I can tell you without a doubt, this is the hardest topic in deep learning. Okay, very complex algorithm, way more complex than the GAN that we saw last week or the last topic. So we'll go over it. I have all the materials. I posted them on Brightspace, and so I'll show you where they are. So you can go ahead here, and let's go to the GitHub. Okay, so under PyTorch, oh, that's not. All right, so you can see here in PyTorch, go to deep learning. Okay, and under deep learning, I created this folder. So PyTorch deep learning transformers. Okay, I added basically the last algorithm. Okay, which maybe we have talked a little bit about it. I created a Jupyter notebook, and basically everything is self-contained here. Okay, so this is the data. Okay, so this is the data that the model would train on. And this is the Jupyter notebook of the deep learning algorithm that goes over the transform. Okay, and I have some images here. So basically, to train this, you will need a GPU, and it would train in 10 minutes. Or if you're using your CPU, it's the kind of thing that you have to run overnight, right? So hopefully, if you run this overnight, the transformer would learn. So this is, as it's called, a decoder only, and I'll go over that. It's basically a tiny GPT. Now, ChatGPT, for instance, is trained on this architecture, except that ChatGPT has a ton of data, and it was trained for like 3 months, basically on the entire internet, right? But it is based on this. So this is literally that. The state of the art is basically this. So this is, as I said, a tiny ChatGPT style LLM. Took about 20 minutes training on my GPU. It would take over a day probably, or overnight. GPT are only the decoder part of the original transformer architecture. So the original paper that proposed this architecture, the transformer, was published in 2017. And it's the paper, you can reference it as Vaswani et al. So the code that I provided here is in this Jupyter notebook. This just goes over what characters we're going to use to predict. This is the training and losses. So if you decide to run this on your own, you can expect that kind of performance. So as you can see, the loss goes from 4.2 and it goes down and settles around 1.4. Okay, so that's something that you can try, but actually it does an okay job. So this is a generative model. So if you remember, we got up to CNNs where we looked at, we've looked at deep learning. Well, we started with regression, then we looked at classification. For classification, we looked at deep neural networks, then we looked at CNNs, right? And this is CNNs is kind of where we took it for as far as classification or feature extraction. And then the last two topics that we've looked at are the generative models, which are generative adversarial networks, which you already saw an example of that. And now another generative model, which if you remember, GPTs are based on images, GANs are generate images basically in general, and then GPTs are used for language generation. So this was trained, this simple little GPT was trained on Shakespeare data, just a very small file, right? So it's not like all the works of Shakespeare. In fact, it was only trained on this file that you see here, input.txt. So if I click on that file, it's kind of big, but that's actual Shakespeare text. So it shows the author, so first citizen, your all resolved rather to die than to famish, second citizen, one word, good citizens, and so on, right? So this has actual structure of like a play where people are speaking and then what they're saying. And the GPT model that you train with this can actually pick up on the fact that there's a speaker first. So it's going to say speaker and then it's going to speak. So it kind of is able to capture not just generating text, but also the structure of this document, which is really interesting. Okay. All right. So that's kind of, like I said, if you run this is our last topic, right? And if you run this on your CPU, I was running it on my laptop and it was just like, it was consuming a lot of energy. So you could see that it required a little bit more, but like I said, you can probably run this overnight and get some results. All right, so that's basically what you can expect. This is actual text that this GPT model generated. So you can see it actually creates authors, so Sixinius or Sicinius, Meninius, and then it says things like come brother with myself and now. So obviously that doesn't make any sense, but it does have some of that sound of Shakespeare, right? So I pray you were sword man's so parted train. So again, it's not grammatical, it doesn't mean anything, but that's only because this model used a very small file to train. The idea with a GPT is that you would give it all of Wikipedia, all the books in the world, the whole internet, and then it learns how to say things very grammatically. But it's basically just like a parrot. It doesn't have any, you give it a token to start with, and then it just starts producing text, basically. Okay, so that's really how they work. Any questions on that? So something like ChatGPT is basically a model that has a GPT and then some additional things after that. It's been what is called fine-tune on question and answering or fine-tune on various other tasks. But initially, a GPT is just an autoregressive model. You say the, and it'll just start saying something, generating text. So that's what we're going to go over today. Just try to understand how that works. As I said, it's a bit complicated, but that's kind of the intuition. I'm not going to require you to do this, as a homework or anything like that, but it's definitely an interesting algorithm. Okay, so trying to think. Yeah, so this is the script that I put together. So you can, it's basically a Jupyter notebook, but I added a whole bunch of notes and things. So it's almost like a chapter in a book, if you want to think of it that way, or at least I'm polishing it to get to that point. And so I'll kind of go over this in a high overview first. So it's called GPT Basics OOP. All right, so I'll start with the introduction of what is a transformer, and then we're going to see that a GPT is only part of the architecture of a transformer. Okay. Now, one thing that should be very interesting to you is that the transformer was created by Vaswani et al. At Google in 2017. And it is now 2023, about 6 years later, and the architecture has not changed that much. There's been like 1 or 2 little tweaks that they've made in the logic of how they do it, but in general, it's exactly the same, which just, it's amazing, right? That it's also been stated quite a lot that the people that created this, when they did it, they didn't even know that it was going to be this successful. Okay. Now, I don't want you to think that I'm saying that this is sentient AI either, right? So it's not. I don't think it is at all in any way, shape, or form. But it is. So if you see me excited about it, it's because I'm kind of a nerd, right? And I love fancy algorithms, not because I think you have AI at your hands. Okay, that's not the case at all. But it's got some interesting things, and it's something that's worth studying, and it's got some very nice ideas. Okay, so, and it is powerful. As you can see, it can generate text, and it has been proven that it can generate a lot of text. Now, how are these models like Llama and ChatGPT done? Well, basically they use this architecture. But whereas I have one file that fits on GitHub, right, is less than 25 megabytes, they have petabytes of data. Like they have internal Google data plus open source data, just all the books in the world. Okay, they have all the books in the world. And that's just one thing of many that they use to train it. They don't use one GPU. I mean, on the CPU, it might take a day or overnight. On a GPU, it took me 10 minutes to do this. Training it with all the data that they had, I think it took them 3 months, and they had 10,000 GPUs. So they distributed. So it's like a distributed architecture. I mean, they have teams just to deal with the hardware. Okay, so it's not a trivial thing to train one of these. Does that make sense? Okay, but what we're going to talk about today is just the architecture and not even the full architecture of the transformer, just one part of it. Although they're both very similar. There's an interaction between one and the other that I'm not going to discuss, but in general, the ideas are very, very much the same. Okay, so that's kind of the big picture. So this, as I said, you can get it from the URL, right? These are your notes that I put together. So we're only doing the GPT part of the transformer. This works. So the GPT uses the decoder only part of the transformer, and I want to show you actually a diagram. So I included this diagram here. Okay, this is the architecture of the original transformer. Okay, this is the architecture of the original transformer proposed by Vaswani. It was originally proposed for language translation. Okay, so the idea was to translate from one language to another. For instance, in this example, from English to Portuguese. Okay, that's what it was invented. And it was some obscure paper, they thought, for language translation. And then from there, it has evolved into all these things, right? So if you can see here, you got basically the whole architecture. This orange section is called the encoder. And this orange section over here is called the decoder. Okay, so it's got an encoder and a decoder. Okay, so the process kind of starts here, okay, with the input that goes in through here. It goes through all these layers. All of these layers are deep, neural networks, right? So they're basically deep learning. So whereas think of it as if we had one hidden layer, for instance, here there's 6. But actually, there's way more than 6 because each one of these encoder layers has layers inside of it, okay? But at the end of the day, a lot of these things are just what? X times Y plus B, and you get a Y. And X times Y plus B, and you get a Y. They're just very deep, okay? And so that's kind of what we're going to get at today and how the transformer works. All right, so the input goes through here, and then you get an encoding here. Basically, the encoding is not something that is meaningful to a human. It's an encoding. It's something that the transformer just learned. Okay, and then that information, if you notice, is this blue line that is fed into all the decoder layers over here. You see that? So part of the encoder goes into all these decoder layers. But here, when you're doing translation, as they did it initially, they took, let's say, the English sentence, and then here they take the Portuguese sentence. So the Portuguese could go in here, gets encoded, but now you have the information from the encoded English. So encoded English, encoded Portuguese, goes through all these layers, and at the end of the day, you predict the word in Portuguese. That's it. Do you guys see that? That's ultimately what it was trying to do. It was trying to translate. Okay, so it would get, the English, the Portuguese, and it predicts the next word in the Portuguese sentence. So it's an autoregressive model, it's called. So let's start with the idea that to train it, for instance, now remember, this is not GPT. This is just the whole transformer. So you would give it, the cat is sleeping on the table as an English sentence, and that's straightforward. That whole sentence gets encoded into something, right? Then you give it the equivalent of that, the cat is sleeping on the table, but in Portuguese. Now, the key thing is when you're training it, you actually give it that here and you give it that here as well. So you always give it the same sentence here, Portuguese sentence here and here. And you might ask yourself, then what's the point of that? Well, the point is you give it the Portuguese sentence here, but this one over here is shifted by one. So every word is shifted. So that I gave you this exercise at the beginning of the semester in the NumPy problems, where I said, grab a vector and then shift everything to the right. That's literally, that's why I gave you that example, is so you had a sense of what is going on there. So what's the point of that? The point of that is you have that cat is sleeping, and then you have cat is sleeping next word, right? So basically, if you're looking at the cat down here, because what you're doing is imagine you're like then the cat is, right? So as it's learning, the same thing is happening at the top, except that you always have the next word. So whereas here, so the easiest thing for you to visualize is if you have the here, then up here you have cat. If you have the cat, then up here you have cat is. Is if you have the cat is sleeping. And so what it's learning is how to predict the next word given the words that it knows over here. Because when we speak in sequence, right? So if I say to you, the car is going very fast or slow, but no one's going to say the car is going very mountain, right? That doesn't make sense, right? In the training, it will never learn that. But it'll learn the car is going, and over here there's no the anymore. It'll just be car is going very. The car is going very fast. You see that? And it's always predicting that last word. Does that make sense, guys? Any questions about that idea? So that's it. That's what the transformer is about. You give it the English, you give it the Portuguese. The English gets encoded through a whole bunch of matrix multiplications of weights. There's something else called the attention mechanism. We'll talk a little bit about that. But after that, the whole point is to predict the next word in the sentence. Okay? Now, if you think about it, now that I talked about this, you can look at the encoder and the decoder and you can break them apart, right? So you can break them in parts. Right? So if you've ever heard of something like BERT, Roberta, etc., those models, those are what are called encoder models. All right. So that means that people just, let's ignore the decoder part and let's just use the encoder. And then they created those models called encoders. And those are BERT, Roberta, Albert, all of those models that you may have seen on Hugging Face. For our class, I will focus more on the decoder because that's the GPT part. And ChatGPT is in everyone's minds, right? It's a more exciting thing. So I wanted to go over that one. In particular, it makes it a little bit easier. And just keep in mind, they're very similar. Okay, at the end of the day, the architecture is very similar. Notice that just like with CNNs, where you had the convolutional layers, right? What did you have after all the convolutional layers at the end? You had a normal feed-forward layer. Remember that? That you have to kind of flatten and then figure out the dimension. So that the transformer also has that. And this is why I have this huge red arrow there, just to indicate that's the flattened last layer, which allows you then to map to the word that you're predicting. Got it? All right, so now let's take a look. So one way to understand these transformers, one good way of understanding these transformers is to basically look at the dimensions, okay? So we want to look at the dimensions here. So if you notice, it starts with n by 40, okay? That's the input to a transformer. So n just means the number of batches. So it could be one batch, and then you just have a vector of 40. Or you can have 16 batches, which is 16 sentences. So 16 English sentences, for instance, right? So what is this 40? What do you think that 40 is? That's the words in a sentence. Now, keep in mind, we don't actually, the term is actually tokens or subwords, because we don't actually use words. Instead, you use what are called subwords, which is the best analogy is like syllables, but it's not the regular syllables that you learn in a language. In fact, these syllables can be calculated through an algorithm based on frequency. Lucas. Exactly right. Perfect. So there's algorithms for that, like sentence, piece, etc., tick token, that will literally give you those syllables. Okay. All right. So, but why do we set it at 40? Well, one thing about the transformer is that the inputs have to be fixed, just like with all machine learning, right? In images, we always gave it 28 by 28, 32 by 32. We always want to have fixed things, because at the end of the day, we can't have matrix multiplications where one time the thing is n by 40, the next time is n by 50 or n by 60. They can't be varying in size, right? Because it's all a consistent set of matrix multiplications. So instead, you pick this value. So in this example, it is n by 40, but I don't think it's n by 40 in the code that I actually have provided for you guys. Okay, so this is just to illustrate. So it's n by 40, so that's 40 tokens. So that means if I have a sentence like the car is going really fast, well, that's not going to be like 7 words, because there's subwords in there, right? Going is probably 2 syllables. You have to break up words into like the syllables or subwords. But 40 should be big enough to hold that sentence broken up into all the tokens or subwords. Does that make sense? So what you do is, if the sentence is less than 40 subwords, you just pad the end. Padding just means put zeros or whatever, and they can be ignored when you do the matrix multiplications. There's a trick that you do so that they just get ignored and not taken into account when you're optimizing things, okay? If for some reason your sentence is greater than 40 subwords, then it gets truncated. So of course you want to pick something that's big enough to hold all your sentences, but at the same time that it's not so big that it'll never run on your computer. Because remember, we are limited by, well, GPU size, hopefully. Okay, but if you're limited by CPU size, you're in even more trouble. Okay, does that make sense? Questions? Nope. All right, so so you have to think, when you think of transformers, in terms of matrices. That's the key thing. And this is, in the text, I try to always put in dimensions. So hopefully that gives you a better intuition of inputs and outputs. Okay, so it's like when you do matrix multiplications, right? You got to know what the input is, what the output is. Now, if you notice, once you read in a sentence, this could be, as I said, n is a batch, so batch of 1 or batch of 16 or 32, doesn't have to be very big. And then 40 tokens, it gets processed, and then it becomes from a square matrix into a cube, a 3-dimensional matrix. So now you add a little bit more and you say n by 40 by 512. That 512 is a vector of size 12 called the embedding. So what's going to happen is, and I'll show you in the code, a word, let's say cat, will not be represented as a string into the transformer. Instead, it's just an ID. It's going to become like an integer number, 3 or 17 or 55, right? That number, then, it's going to be basically, you create an embedding in the neural network that says 17, and all the IDs are actually a vector of size 512. You see that? So that's actually the data. The data is these embeddings that represent each of the subwords that are going to go into the transformer. Now, the question that you might have is, what is in these embeddings, right? That's really what value do you have? So if we wanted to represent the easiest thing that you should be able to think of right now is, if you wanted to represent a vocabulary of 10,000 words as vectors, right? What would you do? What's like the most intuitive thing? Create a vector of size 10,000, yeah? Where every column is what? One of the words. So then put a 1 that corresponds to that word, and everything else is 0. Do you see what I'm saying? So that way, every word in that vector, has a position, an ID, and then when it's it's, and that's the third position, then 3 gets 1, and everything else is a 0. What's the problem with that approach, though? The problem with that approach is that vector is too big, 10,000. It's a sparse vector. Everything's a 0. There are 9,999 zeros in there and only a 1. That's not good for neural networks, right? Does that make sense, guys? That idea? All right. The other thing is you lose sequence. When you're embedding that kind of thing, also you lose context. The word bank of the river, robbing the bank. It's always going to be one ID, 37 for that, So all those things are problems that would make the model not work. Transformers solve a lot of those problems, okay? You pick an embedding of size 512, and then those values initially are going to be random values. This is one of the reasons why the transformer needs so much data, just to learn those embeddings, if you want to think of it that way. All right, so then as you're giving it the IDs of 17, 37, 55, you're actually giving it, you give it as an n by 40, but then that becomes an n by 40 by 512, right? So each of the words now has its embedding of size 512, and they're just weights like everything else. So as the model is learning, these weights are being learned, which means these values are getting filled in. Do you guys see that? And something interesting happens. Okay, something interesting happens. Imagine we don't have a space of 512, but a space of 3 dimensions. So that's this one, right? This room, X, Y, and Z. So if I have cat and dog, right? One of those 3 features, right? Because remember, this is R3, so 3 features. We could be called furriness. Now, did we intentionally say we wanted a furriness feature? No. But the neural network learns correlations, right? And it's going to learn that the dog and the cat have something in common, which is that they have furriness. So that means that, let's say that that's the x-axis right there, right? And that represents furriness. So for dog and cat, that value is what? High. Do you see that? But then we have car. Car, for that feature, does not have furriness, hopefully, right? So then it's a low value on that axis. Do you guys see that? And that happens for all 512 embeddings, or because this is a 512 means that it's a space, R512. So just like we have a space of 3 dimensions, we have a space of 512 dimensions, right? Where all these words are just a point in that, and they're represented in there, and the values are filled in based on what they have in common, right? So furriness becomes one axis. Has wheels becomes another axis. So the dog and the cat would score low on that one, but the car would score high. And basically, these embeddings, the 512, are no longer sparse, but there's a lot of values for all of them. So a lot of information is being captured. Any questions on that idea, guys, of the embeddings? Any questions? Okay, so this becomes N40, then N40 by 512, right? So now all the words have this vector of 512 with value. It's basically initially random, but as you start feeding it the data, these values need to be learned, right? And they become then really good representations of the words themselves in the transformer. Now, all this data is stored in the neural network, which is basically this transformer. And then if you look, the next step is to take N40 by 512, and it runs through these encoder layers, which are literally the exact same thing every time. Think of them, going back, the simplest way that you can think of them is going back to the hidden layers of a neural network. Basically, think of this as X, and then in there, what do we have every time in the encoder layer? A W, right? So then X times W plus B, a Y. And then that comes out, and then in the next one, That's enough. Think of it as H1. So then it's H1 times another set of W's plus B equals another H2, and so on. That's basically in the simplest form what you can think is happening here, except that there's going to be one additional layer in there called the attention layer. Kind of like we had the convolutional layer in CNNs. Here in the transformer, we have the attention layer, which has a slightly different objective, but at the end of the day, it's the same thing. Learn some weights based on this idea of attention and pass it forward to the next step. So if we get into this encoder layer as input an N40 by 512, the output is an N40 by 512. And that N40 by 512 that comes out of this becomes the input to this one, and so on. Until you, at the end, guess what? You get an N40 by 512. It's nice, right? That's basically all that's happening in there. Okay? Does that make sense? Yeah, Lucas. It's the embedding size. So let me take out the all right, so let me turn on the what do you call it? I was sharing, wasn't I? By once. Yeah, I think it was. Okay, so all right, what's an embedding, right? So as I was saying, you have some words that I'm just going to create a very simple vocabulary. The cat, car, go, sleep. Right? So that means I've created a vector like that. Okay? This has 5 words. So there's 0, 1, 2, 4. There's 5 of them. Okay? That's the embedding. So I'm saying that this has an embedding of 5. So I call it R5. It's a vector space of 5. Okay, so basically what do I say? If I have whenever I have the word the, how do I encode it? Right? That's how I encode it. If I have the word car, do you see that? That's an embedding of size 5. If I have the word sleep, that's an embedding of size 5. But this is not a good way of embedding things because, first of all, we wouldn't have 5 words. We would have like 70,000 words. It would be really large vocabulary, a lot of zeros, few ones in there. And so, but this is the encoding. So remember, transformer or neural networks don't understand words, right? But they understand vectors, right? So everything that we give them is a vector. So instead, though, we don't want this approach for embedding. What we want is, we want to have, staying with car, sleep, cat, go, and so on, ... We want, actually, some other type of embedding. We have this goal, right? And I'm going to say, I want this to be 512. That's where that 512 is coming from. So that means this has 512 columns. It's R 512, okay? Everyone with me? But the problem is, before, I was explicitly saying this is always for what? Car, right, very good. This is always for car. I explicitly said that. Instead, what I want nowadays is to say, I don't know what, let's say this is column 103, right, for all of them. What is column 103? I actually don't know. You see that I don't know. But I'm going to let the neural network find some pattern that actually has meaning. This is why I was giving you the example. So for instance, I have car, sleep, cat, and then I have dog over here. So as it's learning and it's updating the weights, intuitively, you can think of this. If this is important, especially if it's learning like to differentiate between animals and vehicles, for instance, right? So then furriness may become an important feature, right? If it's like with images and so on. So it could be that column 103, you can think of it as being a question like, does it have a lot of fur or not? Do you see that? That's the intuition that you can think of it. So then what happens as the neural network is training and looking correlations of the data is that these values for car, this is going to be what? Like, let's say 0.05. For sleep, this is going to be 0.01. For cat, this is cat. This would be 0.980, I guess, 0.80. And then for go, this would be 0.03. And then for dog, this would be what? 90 or something. Do you see that? So now all the columns in these vectors, get a value because the neural network is trying to learn, right? It's trying to learn these embeddings. Okay, and that's the idea. It's just basically, think of it as initially it tries randomly and it doesn't work. And then it tries again and it doesn't work. Eventually, it got this one high and this one high, and the results improve. So the neural network then is going to try to improve those even more. You see that? And eventually, just by kind of accident, it figures out the 103 becomes the feature for furriness. And then there's one over here, if you're detecting vehicles, let's say it's 17, and that it picks up on this has windows somehow. All right, so if it has windows, car starts to get 0.87, sleep gets 0.01, cat gets, maybe because it's got eyes, it thinks those are windows into the soul. I mean, it gets really deep and philosophical. So then it's like 17, right? I mean, this can happen. I mean, I kid you not. I say it as a joke, but if it was looking at text, it might actually, you might see a window to the soul, and then the thing starts to think of it as a type of a window. Go, all right, 0.01. Dog, again, same idea, 0.018. The dog is even deeper somehow, more, a deeper window into the soul. So it thinks it's more, right? And does this make sense? So this is an embedding, okay? This is way much better than this one. This one is terrible. And up until like 2010 or so, this was what everybody did. And then after 2010 came work to vec and a whole bunch of other things. And then now the transformer just does it on its own. It's even more sophisticated than that. But the idea is basically that. So you define just the space, the vector, and what limits you once again is the GPU size, etc. Because you could do 1024, but those are all matrix multiplications on your GPU, so they may not be good at, fast enough. Does this make sense, guys? Lucas, does this answer your question?
Yeah.
Yeah, all right. Yeah, go ahead, please.
Every column of the 5 and vector, does it represent something?
Yes, it should. This is whereas before the previous one is a sparse vector, this is actually a dense vector. So it weights in the neural network, right? So it's think of it that way. So the neural net will learn the weights that are relevant for the task.
Any random.
Right, because it depends on the problem. Remember that what we're learning is a task, right? So we're learning to speak like the GPT, which just speaks, or we're learning to translate from English to Spanish, or you're learning to translate from Shakespeare to Star Wars, something like that, right? The different kind. So it learns these values based on the task that you want. And it's going to be specific to the transformer, not a separate thing.
How does it relate to the 40, the second vector?
Every 40 has a vector of 512. Because every 40 initially is just IDs. We'll go over this in the code, but every 40 is just an ID. So here, car, we don't use actually car in the neural network. We would say 17. And sleep would be 80. And cat would be 3. And go would be 9. And dog would be 105. Those get mapped into a vector of 512, which is actually what is used. So it's a lookup table. Whenever you want cat, it's 17. 17 is this vector. And it gets pulled out because it's like a matrix multiplication. So all the vectors are always there, but when you multiply times the IDs, you only grab the vectors that correspond to the IDs. The other ones get ignored.
And can you have a n value greater than 40?
You have a what?
And the first dimension, n value.
N is the batch number. So you define that, but it's usually 8, 16, 32, 64. So n is the batch number. So it could be 1, but then you're not taking advantage of the GPU power.
And for the 40, we are assuming that we just have 40 words in 1 second.
40 subwords. 40 subwords. So syllables. Think of it intuitively like that.
So for language, will give all the subwords. If we are training for language, it will give all the subwords instead of not just 40.
40 is the sentence size. Think of it that way. 40 means the vector where your sentences fit. So when you pick 40, you're assuming that most of your sentences are actually smaller than 40 subwords. Eventually, you'll find a sentence that is more than 40 subwords, and it just gets truncated. It's like it gets ignored. That part, the last part.
That does mean that the generation of the sentence is under 40.
That's a good question, actually, because I've done this before, and the generation goes up. I can almost say this, the generation of the text goes up to usually the average of the sentence size, which is really interesting. So it learns what an average sentence, the length of an average sentence, and then it generates usually sentences of average length, but they're still correct grammatically. It just uses sometimes it finds a word that's appropriate, but summarizes the sentence. That's actually a really cool thing I've seen. Any other questions on embeddings? It's an important question, so I appreciate your question, Lucas. And it is important, yeah. The way to understand transformers, as I said, is n by 40 by 512, and then, and what is the input, what is the output, okay? Any other questions? So let's keep going. So like I said, I still have the rest of today and the next time we meet to finish this up. I was also trying to do the CGAN, and we still have the competition, which again, please don't forget, you all need to present for 10 classes and do at least what we did with the deep neural network, if not the CNN. All right, so let me go back to the Jupyter. I do recommend that you run that Jupyter at home, okay? All right, so where was I? Okay, so going back to the Jupyter here. All right, so I think I've given you a lot of background, so let's go over some of the notes that I have in here. So Okay, so let's go over here. Because I've summarized a few things. Now the transformer has a lot of things going on, all right? So there's a lot of little tricks going on. So simple GPT implementation in Torch. So the GPT uses only the decoder part of the transformer. What I mean by that is it only uses this part here, okay? And not this one. Okay, implementing the other part is another approach. Joining them is more challenging. And it's harder to understand. So I think because this is the same, very similar to this, I think just doing a GPT is the best way to kind of get a gist for how transformers work. And then maybe you guys can do the encoder and the whole transformer on your own. All right, so let's go over the notes. So the GPT uses the decoder only part of the transformer. The input to the decoder varies based on whether you are training or predicting. And this is true, okay? So if we are predicting, then we give it the starting token and the. And then if it learned a lot about animals, it'll probably start with an animal. But if we told it a lot about vehicles, it'll start with a vehicle. Do you see how that works? So it might say the cat or the dog, or it might say the truck or the motorcycle. It's just, but it's, you know, because in English you have what? Determiner followed by noun and then some verb or something, right? That's kind of the structure. And that's what it's going to try to do. Do you see that? But there's no, in a GPT, there's no, like, I'm going to give it a question and it's going to answer it. That happens later, right? As you take the trained GPT and give it more information, more layers, etc., to answer questions and things like that, okay? The input to the decoder varies on whether you are training or predicting. If you are training, the input to the decoder is basically the sentence itself. When training, a mask is needed here to prevent the model from seeing all the words it is trying to predict. This is called a look-ahead mask. So this is another thing that might be confusing, but it's actually just a convenience thing. Okay, we could say in a for loop, generate the, then grab that the and move it down, and then, you know, add the next one. And that would make the coding harder. So what they do instead is they give it the whole sentence all at once. The car is going, no, sorry, the car is going really fast, and then there was an accident. As an input and as an output, the car is going really fast, and then it had an accident, just shifted by one. But additionally, you have a mask that's changing. So what's happening with the mask is what? It's doing a matrix multiplication so that it only shows a little bit of it as it's iterating, and then it shows more of it and more of it and more of it. Do you guys see that? So in essence, you're not adding words. The words are always there. You're hiding them and then unhiding them by doing the mask multiplication. So maybe if I go to the thing here, go to the whiteboard. Okay. So that's the look ahead mask. And the reason why it's a multiplication of a mask is because, again, you're doing everything in the GPU. And GPUs can only do what? Multiply things, right? So they need to multiply a thing by a thing efficient. Remember, at the end of the semester, I also gave you a NumPy problem where you had to do what? Do you remember multiply times a mask to just get the values under the diagonal? Do you guys remember that? That's exactly what the mask is for. So you have a sentence here and a sentence here, right? And it's just like these words, right? But in another iteration, it might be these words. So then you need these words. You see, so it corresponds like that. And what you're doing is to control what you show is you're always just multiplying times a mask. So the mask for this one would be 111100. Do you see that? So now, if you want to show this, you just always include the mask of what you want to show. And that way you would show this. If you want to show this one, then the mask would be 1, 1, 1, 1, 1, 0, 0. You guys see that? So every time, instead of iterating and in the training, you always just have the mask to indicate what you're going to show. Okay? So that's an additional step that you will have in the process. Mhm. The mask matches, yeah, it matches what it's trying to show. So how does this work? Mask. I think every input will have to have its mask. That's basically how it is. So whenever you're training, you just give it the cat is, and the corresponding mask that goes with it. So that's how you have to create it. Yeah. So it has to be provided. If you are testing, the input is just previous words. So remember, that's the difference. So there's training and testing, okay? So the mask is usually used for the training. For the testing, it's different because there you are actually generating words. So you're going to start with the, and it's going to generate the car. So then the car does become the input again, and that becomes auto-regressive. So in that step, it should be like that. So if you're testing, the input is just the previous words before the word you're trying to predict. You start with a start of sentence token, e.g., oh, I guess I missed something, e.g. SOS, and predict. The predicted word is then added to the previous tokens, and the process is basically repeated. Okay, so that's how it changes between training and testing. The decoder consists of n decoder layers, such as 6 in this example, followed by a linear layer, okay? Each decoder layer has a decoder multi-head attention layer. So that means it's going to have the normal neural network weights times x plus bias, but there's going to be a new thing called attention, which again, think of it as with CNNs, we had a new thing called convolutions, okay? So we'll need to talk about that. So each decoder layer has a decoder multi-head attention followed by a fully connected layer. So that's kind of like, if we go over here, right? Each decoder layer actually is made up or looks like that. Okay, so it's going to have n by 40 by 512, which goes through an attention layer. The output of that goes into a fully connected layer, and that becomes an output of n by 40 by 512. So you're always maintaining these sizes consistent, basically. Got it? All right. Okay, so going. So each decoder layer has a multi-head attention followed by a fully connected layer. The attention layers consist of n parallel attention sublayers that are later concatenated. Okay, so this we'll have to look at in the code, basically. The numbers are 6 and 8 are a choice of the architect. So this is why I said when you do object-oriented, this kind of makes sense, because now you can just create one encoder layer and instantiate it 8 times or something like that, right? And you can have as many objects as you want. All right, so it's 6:20. We're going to take our 10-minute break and then continue with the rest of the code. So I'll just go over some of the main ideas, and then after that, we'll start getting into the code details, okay? All right, so let's take a 20-minute break. Stop the record. I'll pause the recording here.